So, small project, analog instrument with current sense amplifier. And to be exact, it will have two ranges. So what's going on here? I have my old revamped power supply, card link, a load on it, and this instrument is measuring the current through the load. Oops, sorry, on the high side. The current is also flowing through this 50 milliohm resistor, and the current signal is amplified with a current sense amplifier. More on that later. And then the whole thing is fed into that analog instrument. I'm using the inputs that are really raw, connected to the instrument itself. If you want to see the Innards, if you don't believe me, again, card link where I have a look into this very old contraption. Yeah, and this is just in parallel to show me how many millivolts are really on that instrument. Just a control. Now, why I'm doing this. This analog instrument is exactly of the same type as this analog instrument. The only difference is the mechanical dampening of that guy is no longer working. But yeah, that's all. And yeah, how should I put it? When I put together or revamped that thing, I did something very, very bad. Let's have a more detailed look on that instrument here. So this instrument has two ranges, 0 to 400 milliamps and 0 to 2.5 amps. And you select the range using that switch, which is okay. The small project I'm implementing now will also use such a switch. The problem here is, and let me zoom in a little bit more. I'm using here that mechanical switch to switch between two different shunts. So yeah, we'll have to look at the schematic, but they are in the 100 milliohms range or dozen milliohms range, and you see if I just touch that, yeah, put some pressure here on the switch, you can see how the needle is moving. And that's to be expected, because if you're switching resistors in the a dozen milliohms or 100 milliohms range using a mechanical switch, which itself has a contact resistance of a few dozen milliohms maybe, yeah, that's not working. The other problem was that the resistance of these internal shunts are quite high, because I'm driving an analog instrument. And so the idea was to put a nice little current amplifier between the single fixed shunt resistor and the analog instrument. Quite simple. And the switching of the ranges will still take place via a mechanical switch, but it will be on a high impedance path. So I'm switching here now in a line that has 5 to 7 kilo ohms, and their difference of a few dozen or even a few hundred milliohms when wiggling a switch, contact resistance, doesn't really matter. It doesn't matter. And let's demonstrate that. So at the moment I'm in the high range. I have 1.5 amps. Let's get that down to 400 milliamps. Yeah, and you see the scale. I'm really on the start of the scale now. Yeah, 400, good enough. And I can switch here to the other range, to the 400 milliamp range. And I'm at full scale again. And here I have actually to break one connection on the breadboard. That. And now I'm here on full range, 400 milliamps again. So I have only to switch one line. I think that design, yeah, I have to find the schematic. That design actually switched two lines. I only have to switch one line, and I have to switch a high impedance line where the milliohms order of magnitude contact resistance of the switch doesn't matter. That's the whole idea. Yeah, where to start? Let's first have a look at the old schematic for that instrument here. Yeah, that's the old circuit currently in the power supply. Details on that card, if I don't run out of cards, links. Just a quick rundown. I have two shunt resistors here, and through a switch I can determine if only one shunt resistor is in series with the current flow. That would be the 330 milliohms. Or if I have in parallel a second shunt resistor with only 70 milliohms. And of course the 330 milliohm alone is for the 400 milliampere range, and both in parallel are for the 2.5 ampere range. And the second pair of contacts basically just taps the voltage drop across my shunt resistors off to different input of this little perf board circuit on the back of the instrument. So I have a pair of a potentiometer for trimming and a small resistor for one range, and another trimmer and another resistor for the other range. Protection diode, so any higher voltage, yeah, if I forget to switch the ranges, is shorted across and doesn't destroy the instrument. And this capacitor here just, yeah, is a replacement for the missing mechanical dampening in this analog instrument. Again, details, there was already a card and there is a link. That's the new circuit. We have a little power supply here, 3.3 or 5 volt, doesn't matter. It just has to deliver a milliamp or so to that current sense amplifier here. And it's fed directly from the unregulated, filtered and rectified DC power out of the power supply. For the circuit itself, again, card link to my current sense amplifier videos, where I actually build up most of that circuit and explain in detail how I calculate the different values. Quick rundown again. Current is coming in here. I have my 50 milliohm shunt resistor, and through two identical input resistors that goes into the current sense amplifier, which has a current output. And the value of these two resistors here determines how much current is coming out here proportional to the voltage that is dropped across the shunt resistor. Now forget about that part. For the 400 milliamp range, my output current here is calculated to be 51.3 microamps. So I have two parallel paths here, one through the instrument, which will take up 40 microamps, which is full scale for that instrument, and a second one, a little bit tunable, which will take up the remaining 11.3 microamps. If I want to switch the range, that is, I want to measure 2.5 amps going through here, my maximum output current would be 321 microamps. And so I can switch in a third current path to ground, which will take up 270 microamps. Okay, and at full scale 2.5 amps, the voltage here on that rail should be 1.92 volts, plus minus 5%. So yeah, so a little trimming here, and the rest, yeah, parallel resistors, Ohm's law. Nothing, yeah, special about it. But for the one fact that I have here drawn in a 40 microamp, 200 millivolt, 5 kilo ohm, full scale instrument, while there is currently a 25 microamp, 120 millivolt full scale instrument in my power supply. I guess I have to recalculate all the values again, but yeah, that's a major reason why I make these YouTube videos. Because if you tell it to somebody, and even if that somebody is just a camera, you see such mistakes. You see such mistakes. Yeah. Anyway, I recalculate the values. So here is that infernal contraption. And yeah, I will take it out in a second. But noteworthy here, I have already two clamps to get out the rectified and from the main caps filtered supply voltage for the future circuit. And I remembered I have also minus 1.25 negative stabilized supply. That's actually a negative voltage regulator here with a charge pump and diodes. I wonder what I can do with that. The old adjustment board is out. I have two lines here. One is symmetrical power supply, positive unregulated and negative 1.25 volts regulated. Yeah, symmetric. That's very good if you're working with an op amp, like in my case current sense amplifier. And I also put some temporary lines out here to the ammeter, and my positive binding post is now directly connected to the output. Now I close everything up again and we can go back to the breadboard because I had some new ideas about the circuit. So with all the wires coming out of my power supply, I was able to breadboard the whole thing for the real analog instrument, that one that needs 120 millivolts or 25 microamps, not 200 millivolts, 40 microamps for full scale. And yeah, I said I had some ideas with the negative rail that is provided here internally, but I ended up not using it. Instead, I increased the supply voltage of the whole circuit from, I ran it with the other instrument on a 9-volt battery, and I set 3.3 or 5 volts. But I actually run it now on 24 volts, because 24 volts yields the best low swing with that current sense amplifier here. And there was already a card. Look at the current sense amplifier videos about the low swing problem of amplifiers, even if they are rail to rail. Anyway, so 400 milliamps displayed here, 400 milliamps displayed here, 120 millivolts across the instrument. Everything's hunky-dory, and if I go down to cut the load completely, go to 0, then I just have, a few millivolts left. I can live with that. It's not nice, but I can live with that. I wanted to kill that completely with a negative rail, but the problem with the negative rail is that if you switch the power supply off, the negative rail survives much longer than the positive rail, which it should. That's okay. But in this circuit, that has some really funny effects. Anyway, we can go to the 2.5 amp range. Something is wrong. I didn't make the right correct connection. 1.5 amps, that's what my power supply can do. And we are at 1.5 amps. So, and again, cut the load, and we're going down to just a few millivolts, basically nothing. That's less than a hundredth of full scale, what I have here on 0 error. You probably don't see it on camera. I can see it a little bit, but I can live with that. It's not completely perfect, but then it's a very simple circuit with a relatively cheap current sense amplifier. Okay, let's have a look at the circuit diagram again with the final values. So I won't go through all the details again because we already seen that. Basically, this part is unchanged, though the current I'm getting out of the current sense amplifiers in relation to the current going through my shunt is the same. I just adjusted that resistor here, which has to drop more voltage at a lower amperage. Only 25 microamp at full scale going through here now. Now, therefore, if the same current is coming out here, a little bit more current goes through here. So I redimensioned these resistors, and also a little bit different current value for my 2.5 amps. Yeah, it's also kind of a shunt, not like that shunt, but it shunts current away. And the real change, not really design change, but value change, is that I went up to a 24-volt supply here. And that worked out really well so far. Yeah, I guess it's time to make a layout and a board for the whole thing. So that will be the layout. That's of course blown up. I don't know how many percent, a lot. So this is only 2.35 inch by 1.05 inch, the whole board. I mean, it should fit at the back of the instrument. So the instrument screws go in here. These are the big contact pads. Yeah, no wire bridges or links required. Everything is one-sided, very nice, and yeah, so 59.7 millimeters by 26.7 millimeters. Normally, you know, I'm a metric guy, but if I'm working in a layout software, most of the time I do work in inches for some reason. That's what I call perfect. But for the fact that all the holes are missing. But yeah, since I'm drilling it manually, no problem there. Well, oops. On the last stretch, you can actually watch how the copper is slowly receding. And sorry, I can't give you a better shot of that, but yeah, I'm more busy developing the the board than setting up the iPad again on a different position. But yeah, I hope you can see it at least a little bit. And done. Now, that took quite long. Sorry, almost 45 minutes, but the result is... Come on, focus. The result is superb. Yeah, that lettering here is 4 points. The letter size is 4 points. And, oops. Yeah, there was a problem in the mask. But yeah, it's very, very nice. Yeah, the holes, they are 8 thou in the layout, just to give the drill a little bit of guidance. And yeah, you can see them here too. But yeah, maybe so 8 thou, about 0.2 millimeters. Maybe I go for next time for 12 thou, so 0.3 millimeters or something like that. Yeah, second exposure to get the mask off, and yeah, second development, and then yeah, it can be drilled. Okay, I finished the board and I tried to hook it up outside the power supply just for testing purposes. So yes, let's give it a try. Huh? Ooh. Something's not right. I mean, I have 0 amps and I have 89.6 millivolts at the instrument. Yeah, well, give me a second. Yeah, turns out I got the voltage regulator the wrong side around. Not because I couldn't read my layout, but because the footprint and the pattern of the voltage regulator was wrong. Yeah, I don't know why. I can't remember if I used something from a library or if I created it myself. Anyway, it was wrong, so it was not regulating. So we had a full 36 volts here on the power rail, which was not nice. Let's see if our little current sense amplifier survived that ordeal. Looks good for the moment. I mean, I'm on 0 volts, 0 amps, and let's ramp that up. Okay, something's not right because I have no current flowing. But at least the instrument is no longer showing voltage without any current. Yeah, I come back to you. Okay, this time it was a cold solder joint here at the power connector. So not power supply for the board, but where the main current flows through the shunt. Yeah, kind of a cold solder joint because I'm in the habit of gluing down such big connectors with Loctite first before I solder it. And obviously some Loctite went through the hole onto the pin. And it didn't took solder. It looked good, but it was kind of, yeah, how should I show that on camera without implying any sexual innuendo? Yeah, so there was a coat of Loctite around the pin. And so the solder flowed visually around it. Yeah, made a nice puddle, but didn't make contact to the pin. Yeah, shit happens. Third time's the charm. I still have the power supply set for approximately 400 milliamps. So let's see what happens. Oh yeah, okay, that's not a big deal. That's just me. Okay, and of course we don't have 400 milliamps because I've reached out the range switch at the moment, so we are in the 2.5 amp range. So I should be able to go up to 1.5. And then we should be around, yeah. I won't calibrate the thing using the pots. Yeah, it's just a test. So 1.5, that's good. It's still working. My little current sense amplifier has survived 36 volts. Yeah, I won't look into the data sheet, but obviously it was not really happy with 36 volts. Yeah, let's try the other range. So let's go back to 400 milliamps about this, and I disconnect the bridge and the switch. And yeah, we're approximately at 400 milliamps. Yeah, that was my switch bridge. Perfect. And yeah, you see why I like to test the boards outside the unit before I put them in. I mean, yeah, getting something in such a board into something crowded like a power supply, and in addition at an odd position, yeah, at the back of the instrument, and then doing that 3 times, yeah, you see the reasoning behind that, debugging it outside. Okay, yeah, I'll get that thing now installed inside the power supply behind the instrument. Just one close up before I start calibrating. So this is the board now at the back of the instrument, and yeah, the screws are actually yeah, the plus and minus contacts of the instrument. And as always, everything is heat shrink, yeah, and nice and clean. Yeah, my positive from the control regulator board goes in here, and then the other red cable goes to the positive connectors on the front. And yeah, it looks much better than that old atrocity, and it works much better, hopefully. Okay, front view again, and then let's calibrate it and close the thing up and wrap up the video. So let's see what happens if I switch it on. Nothing. That's good, because we are at 0 volts. And can you see that? Yeah, the needle is on 0, so no low swing problem here, but I wouldn't expect a low swing problem with 0 volt output. Now let's go up to 400 milliamps. And I have to change the range. Okay, I soldered the range switch, soldered on the connections to the range switch, obviously on the right pins. Yeah. Okay, and now we can calibrate. And yeah, zooming in a little. Yeah, that's right on 400. Yeah, okay. Let's do it right. That's not exactly a precision current sink there, is it? Um, yeah, this is a little bit fiddly. Okay, come on. That's good enough for an analog instrument, is it? Yeah. Okay, then let's go to 2.5 amps. That is 1.5 amps. Okay. I'm overshooting here a little bit. Come on. Yep. That's definitely good enough. 1.5. And let's see if I switch off the load. Yeah, I mean, that needle is on 0. Okay, so even if I go up to 25 volts, which I'm currently not, but yeah, it's still fine. Yeah. Yeah, that's good. I think I will close, I mean, putting the lid on and putting in 4 screws. I don't have to show that. But yeah, that's nice. But I mean, there are still a whole lot of improvement we can do to especially that power supply. One thing that I saw was the transient response of that thing is actually quite awful. Watch what happens to the voltage if I switch the load back on. Yeah, it catches again, but yeah, this this is not nice. This is I mean, it's okay for what it is. You know, bog of the mill standard circuit out of the datasheet, 317 linear regulator, but you can do better. I tell you, you can do better. But that's for another day. Until then, bye.